Okay, so welcome back to another video. So in today's video we have the following integral. The integral from 0 to pi divided by 4 of the natural log of the natural log of cotangent x dx. I guess some might call it a double logarithm of a trig function of an integral rather. But I can already tell just from first glance that we're gonna have to do a lot of substitutions. There's also gonna be some there's a little constant that we're gonna actually be using, and you might recall that from several videos that I've used this constant. So just to prepare for that, but also we're also gonna be introducing a new function that's never been said or written in this for all the past videos that I've ever done. So this should be exciting. Let me just write our given function. I'll just call that capital Y. So we have that's just equal to the integral from 0 to pi over 4 natural log of cotangent x dx. Okay. Now I want to perform a u sub, so I'll let u equals tangent x. Then you'll see that differentiate both sides. Du is actually equal to secant square of x dx. But I can actually use the following trig rule, and that du is simply, well, secant square x is actually just equal to 1 plus tangent square x dx. I'll divide that by both sides and we get that du is equal to, or excuse me, dx is equal to 1 divided by, now we have that tangent square x, that's the same thing as u squared since we have u is equal to tangent x, so it's just 1 divided by 1 plus u square du. So now we plug everything back in. So our new integral, see, we plug 0, tangent of 0 is actually just going to equal 0. And if we plug tangent of x for x is equal pi over 4, we get that that's just going to equal 1. So then we have the natural log of the natural log of, let's see, cotangent x is the same thing as 1 over tangent x, so I can write that as 1 divided by u, and then multiply with our dx substitution. Now if I just simplify this out, then I can just get that this is just, see, the natural log of 1 over u, and then divide that by 1 plus u squared du. And now note that since our the absolute value of x is strictly less than 1, because that's like the bound we're integrating between, we see that we can actually write 1 over 1 plus u squared. Let me actually replace this x with a u instead. We see that we can actually write this as the following Taylor series, or not really Taylor, but the series expansion. That's the infinite series, n is equal to 0, and this is -1 quantity to the power n multiplied by u to the power 2n. Okay, so with that, I'll just substitute the 1 plus u squared back in with our series. So, okay, so 0, 1, ln of 1 over u, then multiplied with our infinite sum, -1 n, and then u 2n du. All right, it's also convergent too, so this means I can actually just move the summation outside the integral, and then -1 to the n, that's constant, doesn't depend on u, so I'll also move that outside as well. And so we have 0, 1, let's see, so it's u to the power 2n, and then multiplied by ln of 1 over u du. Okay, good. So now let's actually perform another u substitution. This time, let's just call this t. So t is equal to ln of 1 over u. Okay, so if I do the following, so that means we have that dt is equal to -1 divided by u du. Let me actually because we have u that we want to substitute with t, so let's actually solve for u to substitute that. So let's see, I can actually take the exponential to both sides, so then this is just let's see, this is just e to the t is equal to 1 over u. So therefore, this means this is just u is equal to e to the -t. And so I'll plug the u back in. So, well, actually, rather, I'll divide the negative by both sides and then multiply the u. And so we get that that du is equal to negative, it's a negative over here, negative e to the power negative t dt. Now we do our following substitution. So we have our new integral, and then we have to plug in our new bound. So when 1 is equal to u, that means this is just ln of 1, that's just equal to 0. And then when we plug 0, 1 over 0, clearly that actually, you can see that that's going to approach infinity. So that's infinity over here. And then plug in back, so u is equal to e to the negative t, so, okay. Then to the power 2n. Then the natural log of, so we said the natural log of 1 over u is t, so just put this back to t, and then substitute back our du substitution, which is the negative e to the power negative t dt. We substitute this back in. Now notice that I'll change the bound of integration, since 0 is the upper bound and infinity is the lower bound. You know, that can't happen. So this means you have to change the bounds. That'll become a negative. But we also have that there's a negative with our negative e to the negative t, so that'll cancel. And what I can do is, because there's the same base of e, I'll actually combine this under one base. So rather, this is actually going to mean that we have that this is, well, let me slow down a bit. Let me write follow. So this is e, then distribute the 2n over here, so this is negative 2nt multiplied by e to the negative t, and then ln of t dt. Simplifying that expression now, we get that this is 0, infinity, and I can actually factor out a negative t from here, so this will be negative t. Rather, I'll write it like this. This will be negative quantity 2n plus 1 multiplied by t, then ln of t dt. So now, guess what? We're going to do another u substitution. This time we're going to call this one w. So now we'll let w equals 2n plus 1 multiplied by t. So then dw is equal to just 2n plus 1 dt. And so therefore we have that, I think I got the room, yeah. And therefore I'll just divide this by 2n plus 1 both sides. We get that dw divided by 2n plus 1 is equal to dt. Let me make sure that there's anything we need. Also, we want this in terms of t, so rather that means we also get that t is equal to w divided by 2n plus 1. Okay, good. Now we have all the substitution that we want to use. So then, doing all this, okay, so we get the following. Let me actually write this in red this time. So we have, okay, so we have our new integral. So when we plug 0 for t, that's just going to be 0. And then when we plug infinity for t, that's also going to be infinity. So bounds haven't really changed in this sense. So now we just plug everything back in. So let's see, this will be e to the negative w, okay, and then multiply by ln of, we set ln of t, so t is actually going to equal to w divided by 2n plus 1, and then substitute back for our dt, where we said dt is equal to dw divided by 2n plus 1. And then what I can do is I'll actually just factor out the 2n plus 1, so we get that this is just 1 divided by 2n plus 1, and multiply with our integral from 0 to infinity of e to the power negative w multiplied by ln of w divided by 2n plus 1 dw. Okay, next, I can actually use our rules of natural logs to write this as a difference of two natural logs, but just be careful that we actually have to distribute this later, so let me take it slow and write it this way. So this is the integral from 0 to infinity of, let's see, e to the negative w ln of w, and then distribute the e to the negative w for the 2n plus, the natural log of 2n plus 1. So then this is minus e to the negative, or e to the power negative w ln of 2n plus 1 dw. Now, what I'll do is I'll just distribute the 1 over 2n plus 1 to both to all the terms. So then we get that this is 2n plus 1 integral of 0 to infinity. I'm just going to write ln of w, and then this is just e to the w dw, and then minus, I can also factor out the ln of 2n plus 1. It doesn't depend on w in this. So this is the natural log of 2n plus 1 divided by 2n plus 1, then the integral from 0 to infinity of e to the power negative w, and then dw. Okay, so let's actually start with the easy. Now we have to calculate our definite integrals. Let's start with the easy one. This is really easy to show. So let's see, we have 0 to infinity e to the negative w dw. You'll see that if I do u sub, we get that this is just e to the negative e to the power negative w. Evaluate this from 0 to infinity. You'll see that if I plug infinity, so we get e to negative infinity, that's just 0. And if I plug 0 for w, we get e to the negative 0, that's just 1. So we get a negative 1, so it's 0 minus 1. So we get that this is just 1. So then it's just a constant itself. But also notice that 0 to infinity, the natural log of w divided by e to the w dw. As I mentioned, we've actually used this constant before in several videos. This is actually known as the Euler-Mascheroni constant. However, this is actually going to be the negative of that constant. I did a little video on this proving the equality. So if you want to check that out, I'll put that in I'll put the link in the description below. But that's already established. I'm not going to go through the proof again a second time. You can just watch that video. Now that we have our values, now let's actually just plug them back in. So this means coming back from here, now go back to the red. That means this is negative gamma, then divided by 2n plus 1, and then subtract that with the natural log of 2n plus 1, then divided by 2n plus 1. Okay, good. That is our integral over there. So really, I should also say that this is actually equal to, let's see, 0 to 1 of let's see, u 2n, and then the natural log of 1 over u du. So we have that. So now let's actually just plug this back in. So let's see, we're gonna go back to over here, right? So we showed this. So that means let me actually just reestablish what we have. So the infinite sum, negative 1, and then the integral 0, 1, then u to the power 2n, ln of 1 divided by u du is simply just equal to, so back with the sum again, and then just substitute this back in. So negative gamma divided by 2n plus 1 minus ln of 2n plus 1 divided by 2n plus 1. Now to just distribute that in. So this means distribute the negative 1 quantity to the power n. I'll get that. So I'll factor out a negative gamma outside of our infinite sum. So this is negative gamma, and then our infinite sum, n is equal to 0 of, let's see, negative 1 to the power n, then divided by 2n plus 1, and then plus, simply because there's a minus here, so it's a negative 1. I'll group that back into here, so that means we have a degree of plus 1. So then this is negative 1 to the power n plus 1 of the natural log of 2n plus 1, and then divide that by 2n plus 1. Okay, put it simply, let me just write this as a sum. So let me get rid of that, and then I'll put the sum of another infinite sum over here. So this is n equals 0, and then, like I said, negative 1, n plus 1, natural log of 2n plus 1, then divide that by 2n plus 1. Okay, cool. Now, what's the next step here? So we're actually going to recall a new function. And like I said, this has never been mentioned in this video, and also this will be the first time. This is actually going to be the Dirichlet beta function, and that's defined as the following. So beta of s is simply just equal to our infinite series, negative 1 to the power n, and then divided by 2n plus 1 quantity to the power s. Okay, so you see that, well, Okay, let's actually do another. Let's actually take the next step, and let's actually take the derivative of our beta s. So I'll move this over here. So beta s is just equal to. So I'll actually rewrite some things a bit. So let's see. So 0, and then let's see if I were to write -1 and then 2n plus 1 to the power negative s. Then that means if I were to take the derivative, then this will be the infinite sum, n is equal to 0 of, let's see, -1 quantity n plus 1, and then so this will remain the same, but also have to multiply with the natural log 2n plus 1. Okay, and then continuing further, I can actually just simplify this out as let's see, -1 n plus 1, and then natural log of 2n plus 1, then divided by 2n plus 1 quantity to the power s. Let me write that a little better. Now notice that if I were to plug s is equal to 1, so s is equal to 1, beta of 1, you'll see that this is actually going to match with this term right here. And if I plug beta prime of 1, so if I plug 1 into here, that means we get the similar formulation that it's going to equal this. So we can actually just replace some things. So that means, well, also, before I go any further, we replace this stuff. Let's actually evaluate the special values of beta 1 and beta prime 1. But I'm not going to go to the calculations of that. You can actually find the resources of it. Just note that right here. Note that beta of 1 is equal to pi divided by 4. You can see that, right? Yeah, you can see that. Let me write this just a little down. It's because of the light. It's something I can't do under my control. Okay, and then beta prime of 1 is equal to pi over 4 multiplied by gamma plus 2 ln of 2 plus 3 ln of pi, and then subtract that with 4 ln of gamma 1 over 4. So we have those following special values, so we can plug that in. So let's see, going back to here, I'll draw the arrow. We see that that's actually just going to equal to negative gamma multiplied by, when I plug s is equal to 1, then that's actually just beta of 1. And then add this with, plug 1 into here, we get that. So this is just plus beta prime of 1. Okay, and now we can actually plug our terms in with these special values specifically. So we get that this is negative pi times gamma divided by 4, and then plus pi over 4, then gamma plus 2 ln of 2 plus 3 ln of pi, and then minus 4 ln of gamma 1 over 4. Okay, so if I just distribute some things out, I get that this is pi over 4 gamma, then plus pi gamma divided by 4, and then plus pi multiplied by the same thing, 2 ln of 2 plus 3 ln of pi minus 4 ln of gamma of 1 over 4. Okay, but you'll start to see that these terms cancel out. Okay, and then we're just left to evaluate this. So that means pi over 4, and then let me actually use some log rules, so we get that this is ln of 4, and then plus ln of pi cubed, and then minus ln of gamma to the 4th of 1 over 4. Now if we use natural logs again one more time, we get that this is the following. This is under 1 natural log, so this is equal to pi over 4 multiplied by the ln of, let's see, it's plus, so they go in the numerator, so we get that this is 4 times pi cubed, and then divided by, so this is minus, that it's because of the minus, that's why it goes in the denominator, divided by gamma to the 4th of 1 divided by 4. And there we have it. That's our final answer. drawn in this black box like so. Okay, that's pretty cool if you ask me.